All right, so it's my great pleasure to introduce Marcus Zyman, who's going to speak about the joint work with Steve and Cambridge.
Nice.
And he's part of Manhattan Community College and is going to speak about localization of nilpotent R-powered groups. Thank you, Marcus.
I'd like to thank Laurent for inviting me, and I'm sorry I haven't been able to come to the talks, but I was baby duty on Friday mornings, so it's been tough, but it's great to be here. And I will be talking about localization of nilpotent R-powered groups. It's a paper that Steve and I wrote, and we think it's interesting, and we hope that you think it's interesting. So here's my plan. I will give a brief introduction, very brief, about just the classical localization of nilpotent groups. So I'll tell you what that is. If you're not an expert on nilpotent groups, that's at least you've seen the definition, I'm hoping, of what a nilpotent group is. And if you haven't, let me know, and I'll remind you what a nilpotent group is. So anyway, you'll tell me in due course. The second thing I will talk about is nilpotent R-powered groups, then some background definitions, things we had to come up with for the rest of the paper to flow nicely. I'm going to talk about local groups in the context of nilpotent R-powered groups, omega maps, localization functor in this wider category, and there's an interesting connection between residual properties and omega localization, and I will talk about that. That was kind of the key realization we had. So if I have time, I'll get into the proof of one of the main theorems. I will characterize omega local groups in a certain way, and further research. So the further research part is for anyone to think about if you're interested.
You gotta see me first.
You need to check in with Steve before you do any further research. Okay, so let's begin with localization of nilpotent groups. So the first thing I want to mention is, so every group has a lower central series, and if the lower central series ends, if you start with so G is gamma 1, and then the derived group is gamma 2, and so on. The derived group is the commutator subgroup. And so you continue this process, and if you get to the identity, then you say that the group is nilpotent. Yes?
I think it's just to make the point between solubility and this, your commutators would be that the commutators are n commutators. I mean, they're not commutative, but they are n-fold commutator.
Right. So exactly. So
let's define gamma.
So
n plus 1.
So gamma n plus 1 would be G with gamma n.
Okay.
So that makes everyone happy, I hope. So that's the way the lower central series is defined, and you get to the identity. So I will assume that we know what a nilpotent group is from now on, and we say that a group is p-local if nth roots exist, where n is relatively prime to the elements of p, and what is p? Capital P is a set of prime numbers. So that's the definition of p-local. Given a nilpotent group, there is a homomorphism of nilpotent groups that takes G to G sub P. And this homomorphism P localizes the group. What that means is that GP, in a way, is the best approximation to G among all nilpotent P-local groups. And I will define this precisely when we get to the R-powered part. And you will see that there's a precise definition of this. It has to do with a universal mapping property. You want to see an example. So right away there's an example. Take a single prime, little p. Z, the additive group of integers, it's an abelian group. It's an nilpotent group class 1. You can localize it this way. So the localization is actually, it's going to be a subgroup of the rationals. And essentially what you want to define is you have all the integers m, and you want to make sense of division by n, where n is relatively prime to p, if p is a single prime. So E is the natural embedding, and ZP is the localization of Z, the P localization of Z. Okay, so that's an example. And what I'm telling you is really a long story. There's a monograph by Reuteberg, Hilton, and Mislin about localization of nilpotent groups and spaces. So, so bullet number 2 is really a big deal to show that there's this localization functor. And this one is also very interesting. The nilpotency class of the localization never exceeds the nilpotency class of G. So it's kind of a nice functor. And then of course, we get an exact functor. We get exactness from the category of the groups to itself.
Can I say one thing?
Oh, sure.
So the class, nilpotency class, is what the n is to make that gamma 1.
Right, exactly.
Basically.
So you keep going. If gamma C plus 1 is 1, then the class is C. Okay?
So when you speak about this functor, you're taking the category of nilpotent groups into this category of
P local nilpotent.
and this functor is
It's exact. So a short exact sequence
Yes.
will take you to a short exact sequence. And you actually have, let's say you have G from G to GP. No, sorry. So say G to H. Then you can localize. You get all the nice things that you would expect. So this is phi localized. So you get so it's a functor. And this diagram commutes always, right?
Do we know the class of nilpotency of GP?
No, it's just never more than.
It's just never more,
It
but
will
you
never
can't
be more.
compute it.
Well, you can. You can get a bound on it, and in practice, you don't look at the localization because it's too messy. So you look at homomorphisms. You study properties about the nilpotent groups themselves, rather than the P local.
But it's fixed. If G is nilpotent of class C, and for fixed prime, it's always the class of nilpotency of GP.
Well, it
could be different.
It's going to have a class. It may be less. It may be the same, but it will never be more.
So I'm just saying, if you have G nilpotent of class C,
Right.
right?
Localize it.
Localize it GP.
It could be C or less.
It could be.
It could be C or less.
Yes, but is it, for example, suppose it's T. Is it always T, or it could be different?
What do you mean, suppose?
It varies depending on your class of G that you chose.
Okay, so it depends, and it's
It depends.
Oh yeah. It depends on the class, right?
Probably with the
class
dimensions.
and the P.
Yes,
Mhm.
yes.
That's
Because
all.
different G's have different
And
classes.
the prime 2, for example, is a tricky prime. It depends where you localize.
And it's invariant under the class and P. That's what I'm trying.
Yes.
Yes.
Mhm.
One last question about this category.
Yes.
Your objects at the bottom, the GPs and the HPs, do the P's have to match in this category?
Yes. Yes, absolutely.
Okay.
P. Okay. So little p is a single prime in this picture.
Yes.
But p could be a set.
So
of
this
primes.
is actually just, so you have different categories and you
For every p, you have
Yes.
a
Yeah.
category. But also you can talk about capital P as a set of primes, and you can localize at a set. And in that case, this picture will have to do with a set rather than a single prime. And in our work, we look at sets of primes rather than just single primes. Okay,
Thank you.
you're welcome. Okay, so let's see. Hello. So a little more on this. Interesting facts. The restriction of localization to the lower central series will give you localization maps as well. So if you take E to be the localization of G, and you restrict it to the lower central series, that's going to localize gamma I for every I. And then there's a theorem by Hilton, which is quite interesting. What about the upper central series? Well, only if G is finitely generated. And again, this is a long story. This Hilton proves this, and Steve and I were wrong about this before. We didn't
How
understand
did I get
this
into
theorem.
that?
Let's not get into that. We're never wrong. Anyway, there are natural notions of P torsion, P monomorphism. So everything is relative to P. So we're localizing things. In a way, we're studying local data. And the main thing about, I will get into these definitions. They are slightly technical. What's a epimorphism? What's a p-monomorphism? But we'll get to that in the context of nilpotent power groups. And this is a theorem, and the theorem is, so suppose you take the homomorphism from G to K, and you want to ask when is this a p-localization map? It's going to be a localization map if and only if this one is p-local and this is a p-isomorphism. And I'm withholding information. I haven't told you exactly what a p-isomorphism is, but I will tell you at some point. It's a nice theorem in the classical theory. So what else? Well, an nilpotent group is not determined by its p-localizations. And that's, people thought it could be, right? If you localize a nilpotent group at every prime, and you get isomorphisms, does that mean that, or rather, if you take two nilpotent groups and you get that, you localize them at every prime and you get isomorphisms, does that mean that the groups are isomorphic, right? The answer is no. And here's an example of Remeslenikov. This example, you think of S and T in the category of class 4 nilpotent groups. So these are one-relator groups in the category of class 4 nilpotent groups. So you have all the nilpotent relations in there. So fivefold commutators are 1, for example. And it turns out that S and T are not isomorphic, but their p localizations are isomorphic for every p. I have a little calculation on that. It's not terribly difficult to check both things. S and T are torsion-free also. You can check that. So you can localize and you will get isomorphisms, but S and T are not isomorphic. It's kind of a nice counterexample.
Good-looking example.
And by the way, you can replace
Yes.
what is
We
this?
love that.
It's a good-looking example.
It's a good-looking example.
Yeah.
3 and 2 can be replaced by P and Q, where P and Q are primes. Just multiply P times Q, you get PQ. Okay. So let's talk about nilpotent power groups, and that's why you came here. Or I don't know why you came. Anyway, I'm glad you came. So nilpotent power groups.
You might be disappointed if you find out.
Okay, so let's talk about what a binomial ring is. R will be a ring, so this is an algebra colloquium, so we're going to be talking about rings as well as groups. So first of all, what's a binomial ring? It's an integral domain for which this binomial coefficient lies in the ring. And this is what a binomial ring is. And well, there are examples of binomial rings. Steve would know a lot more, but the integers, that's a binomial ring, right? Any field of characteristic 0, that's a binomial ring. If you take f of characteristic 0 and you take a polynomial ring of any variables you wish over f, that's a binomial ring. So there are many binomial rings. So for example, take the field to be q. So the polynomial ring over q, that's a binomial ring, and Steve wrote a thesis about that. Not about that, but that's a big part of his thesis. Right, Steve? Yeah. Okay, so what's an nilpotent or power group? Now, this is a sort of a, we were trying to generalize this idea. So if you have any group, what's the notation G to the nth? Well, that means what it means, where n is an integer, right? So we want to generalize that. We want to make the ring act on the group. So we want G to the alpha to be well defined in the group where alpha is a ring element. Okay, so, but we need certain axioms. So the first axiom we need is that all the laws of exponents hold, right? So we definitely want that to happen. The second thing we want is conjugation behaves nicely relative to this action of the ring on the group. And the third axiom is the Hall-Petrescu axiom, which is, turns out it's needed for many things, but in particular, what's the Hall-Petrescu axiom? This is a theorem in the classical theory of nilpotent groups. It's